roll in today. So it's a pleasure to introduce Thomas Hillen, who I've known for quite a while now, right?
Yeah.
So Thomas, you know, I don't need to go through all. You know, he was president of the CAMES and also is distinguished field visiting professor. And now I was sort of going to write a whole thing, and then I looked at his website, and you know, he sort of goes like that. You see, we want you, and it reminded me of Lord Kitchener in the Second World War in Britain. You know, the posters of Lord Kitchener going,
"Yeah,
England wants you." You know, so to join the army. You know, and I started thinking, you know, if only Thomas had been born in the U.S., you know, we could have shipped him down there to run for president. I mean, you have the experience now, presidents who came to, so.
Yeah, that's comparable, I think. Yeah.
So anyway, it's a pleasure to welcome him. He's going to talk on oncolytic virotherapy.
Yeah, thank you, Steve. Yeah. Yeah, thank you all for coming, even though it's raining. It's a great honor to be here and to talk on and congratulate Steve to your wonderful career and to your birthday. I'm not a student of Steve's and I'm not a postdoc, and we never wrote a paper together, but I might have reviewed some of your answer grants. So I cannot talk much about my past with Steve, but I can talk about the present. And so presently what I'm doing is I'm making interviews with researchers in mathematical oncology, and I post them on a YouTube channel. And I want to show you one of them. So here you go. Okay. So wonderful. So I'd like to welcome my interview guest for today, and then always an introduction with the potential in athletic related insight, even 3 months in this. So let's start it off. So yeah, I'm not going to play the entire thing. Just want to advertise. So feel free to go online, find it on YouTube, and then. So why is this plugged in? Can I take it out? Let's see. Yeah, this works. Okay. So yeah, go online, find it for yourself. It's about 12 minutes or so, and then you can also find an interview with Paul Macklin. And I will update this as we go along and as I meet people and add more interviews to this. So, okay. So this morning we talk about oncolytic virotherapy, and this is collaboration with 3 female scientists. So this reminds me maybe to talk a little bit about this EDI thing. So we always are concerned about how do we support people in underrepresented groups and also in particular women, etc. And I think there are 2 ways we do this. So one is we write grant proposals where we have an EDI section and we write something. I did this for this field thematic program as well. But then the other thing is actually in your daily life to really do it. And I think one way to support women is to work with them, just to work with them, and this and publish, and this really helps, I think. So Awa Babdullah, she finished her PhD in June. She is from the United Arab Emirates, and she is the first math PhD or the first female math PhD in her country. That's absolutely amazing. And then she got a faculty position at the United Arab Emirates position where she is now. And so she's the first female math faculty in her country. That's absolutely amazing. So yeah. Negar Muhammad Najat, she was here the last 4 weeks. She is a PhD student just starting her 2nd year. And Morgan van Walsum is an undergrad student who came over the past summer, and we worked together on oncolytic virotherapy. So what I like to do in this talk is talk about oncolytic virotherapy, summarize what kind of modeling has been done, and then I'm going to solve a small problem, an intermediate problem, and a big problem. So, so keep your eyes open. All right, oncolytic viruses are genetically modified viruses that selectively attack cancer cells and leave healthy tissue unharmed. And there are already two viruses accepted by the FDA. There's a herpes virus for melanoma treatment, and there's an adenovirus for head and neck cancer. And I will focus in my talk a little bit later on the reovirus family and try to do some modeling on the reovirus. Here's a schematic of the function. So we have the oncolytic virus in healthy cells. It can actually enter, but it cannot reproduce in the healthy cells, so they are undamaged. In cancer cells, they use the cell machinery to replicate in the thousands, hundreds or thousands, and then the cell lyses, new virus particles are released. And then this leads to two major effects. And what is this one first? Destruction of the tumor microenvironment, infect more tumor cells. So this one is the first effect. The virus infects tumor cells and then they die. Okay, so there's a direct killing of the virus infection. But of course, this takes time for each individual cell. The second one is it initiates a systemic anti-tumor immune response. So at some point, the immune system comes in and it kills the virus and all cells which are infected by the virus. So then the virus acts like a marker, like an antigen of a cell being infected. So the immune system kills it. But then this immediately leads to a conceptual problem. And that is, if the immune system is too quick, it will kill all the virus before it had a chance to infect all the cancer cells. So we need a highly efficient virus which can invade into the cancer tissue, infect as many cells as possible, and then the immune system coming in and clearing everything up. So the modeling of oncolytic virotherapy is well established, so lots of work. I found out only recently that one of the first papers was by Hillen and her group in 2001. Dominic Vodas wrote a nice paper in 2003, but I think the research started around 2006. And then Friedman and Tian was a postdoc at the MBI from Avner Friedman. They wrote a series of papers about these models, mostly from a more mathematical point of view. Timmy, Tracy Jackson, they included the immune response in these models, and there's a series of papers here. And then what I base my work on is the work of Peter Kim. He was here last week. Polat Wand is a student of Peter. And they also worked on oncolytic virotherapy, in particular for adenovirus. So this is the outline of my talk, which goes through essentially 3 papers. Depending on the time, I might not be able to get through the last one, but we will see. The first one is a paper with Awa in Bulletin of Mass Biology. The second one is a paper with Awa and the Shmulevitz lab, which is in revision in +1. And then the last one with Morgan van Walsum is just a manuscript. And we have to see if this is going to be a paper or not. So we will see. All right, let's jump right in. So I'm going to use differential equations, ODEs, PDEs. And here is the base model for oncolytic viruses. So it's very simple. We have cancer cells, infected cells, and virus particles. Here's a logistic growth term with a competition term between cancer cells and infected cancer cells. Here's the infection term using a mass action. The infection term then goes to the infected class. These cells die with a certain rate because they're infected. And then when they die, they produce new virus with this term. And here an important parameter is this B, which is the burst size. So this tells you how many functional virions you get out of one infected cell when it bursts. Then there's a virus loss term. And then this term in red is already the first discussion point, which I call my small result. Because experts argue, do we need this term or not? So what does it say? It is the infection of virus to cells, which then is removed from the virus particle compartment. So I would say the virus compartment is huge. You have billions of virus particles, and you have hundreds of them binding to a cell, or maybe tens to hundreds binding to a cell. And through this process, of course, you lose 100 virus particles. But in the order of magnitude of the virus particle compartment, this term is actually 0. It's essentially, so I would just say this term is 0. It is very, very marginal.
You don't like it.
Exactly. Other people, though, think it's an important term and put it in. So my first exercise then is just to see what this term does and if it changes the dynamics. Before I do this, I do a little non-dimensionalization to get rid of a few parameters. And now theta is the burst size parameter, which I will then use as a bifurcation parameter. And then it has all the other parameters in there. So the B, the burst size, the L, carrying capacity, tau was the growth rate, alpha is the death rate of infected cells, etc. So this theta will be my bifurcation parameter, and it's essentially the burst size term. Okay. And so here is a typical bifurcation diagram for these kind of systems. So let me walk you through this a bit. Oh yeah, and you see two curves. One is with the kappa term and one is without. So it's a predator-prey system, yes. Oh, very good. Yeah, I wanted to make this point as well. So it's a predator-prey problem and a prey model. And Natalia talked about predator-prey models yesterday in her talk, which is really nice. And she put it in a spatial context using a grid or a patch. And I will put it in a spatial context later using a diffusion. Okay, but we come to that a bit later. Okay, so what is what? So the red curve is the base case, which means kappa is equal 0. And the blue one is when kappa is equal 1. So that's the blue curve. So what you have here is for low values of B, the burst size, you have just the cancer equilibrium, which is stable. But then you get a transcritical bifurcation here, and then you get a coexistence steady state. And here we have a Hopf bifurcation, and then you get periodic solutions. So these ones are these here are periodic solutions. Here's a little, I think that's probably a numerical hiccup. Yes, Hermann. That's a very that's a very good question. I saw this yesterday and I thought, what the heck is going on? So 24, 45. So then here would be 110. No, this is 4, 5. And this is 24. Yeah.
That's right.
There are two markers, right? On top. Yeah. I left it in there so to see if you are really looking or not. So yeah. But then important, the difference between the curves is really marginal, right? So the value for the transcritical bifurcation is different if you have the kappa term or not. The qualitative behavior is essentially identical. So that's the point I want to make. In particular, here in the Hopf region, it is really the same. Okay. All right, so we use parameters from Pouladvant, which estimated these parameters for the adenovirus case. And in this case, the theta value, you remember this was a ratio of all these weights, is 58. The Hopf bifurcation is at 338, okay? So then if I go back, then the base value would be somewhere here. And the Hopf bifurcation value for those parameters is about 338. Okay. Here, if you plot them over time, yeah, this is nothing's astounding happens. So if theta is below the Hopf point, you get convergence to a homogeneous steady state. Whereas if theta is beyond the Hopf bifurcation, you get these oscillations. But interesting here is that the oscillations go very close to 0. So if you look at the cancer cell density in red, okay, so it is virtually equal to 0 here and here again and here again. And the infected virus, the infected cancer cells in black, very close to 0, and the virus also very close to 0. So then you're wondering, right? You have an ODE. ODE modeling is useful if you have large cell numbers. But if you get low cell numbers, maybe you have to do a stochastic modeling, right? If you have just 100 or 10 cells left, they can die just by chance. And one way to do this is the tumor control probability. So we're going to use the tumor control probability to see if we get close to 0, is there a probability to actually have cured the cancer? So here's a little formulation for the tumor control probability. So you compute the surviving fraction, and you put it in where C0 is the initial condition of the cancer cells. And then e to the minus C0s would be your tumor control probability. And I plot this here for different theta values. And you see for the base case, it jumps up high first, but then it settles on about 40% treatment success. Whereas in the other case, it reaches 1 after each period. In particular, here we have a long stretch of 15 days or so where it stays at 1 and then goes down and goes up again. Yes?
The previous slide,
Yes. A damped oscillator? That's exactly right. Yes. Yes. So indeed, so you have a stable equilibrium, but this is a stable spiral. So you oscillate towards it. So you can see already a shadow of the upcoming Hopf bifurcation. And you can formulate it as a harmonic oscillator, yeah, or a damped oscillator. So this is why also Dominic Wodards looked at this already. This is why people say the oscillating state is a good state. This is where you want to be, because you get the tumor density very low and you get the tumor control probability very high or very close to 1. So to get there, of course, we need to increase theta, right, somehow to get into this area. Okay. So now include space. So I come back to what Natalia said yesterday. So we have a predator-prey model, in this case, the oncolytic virus model. And we want to put this in space. And then the question arises, you have, let's say, a two-dimensional domain, and at each location you have an oscillator. And so how do they communicate? Well, they communicate by diffusion. But what does it mean for the dynamics on this tissue? So we know that spatially coupled oscillators can lead to anything. Like there's a Kuramoto model, there's work by Arndt Scheel and Sandstede and Strogatz as well, where you can have like target patterns, you can have spirals, you can have chaotic patterns and all kind of stuff. Okay, so that's what I would like to look at. And the first case would be a one-dimensional situation. So just look at the first row here. I'm plotting the cancer cells in shades of brown, the infected cells in shades of blue, and the virus goes in rainbow colors. And we inoculate the virus at the domain center, and time goes down. And then we see how the virus spreads very nicely with the traveling wave, with a constant speed over the domain. And then we settle here on the coexistence equilibrium or the endemic equilibrium. In the Hopf region, when theta is 500, we get periodic solutions. And you also see they spread out a bit faster. And then if we run this longer, which we did, they fully synchronize. So they go up and down all together, and then they go up and down all together, and they go up and down all together. Okay. All right, so this happens here. Now we tried a different inoculation pattern. So if we have instead of 1, maybe we have 5, which we did here. Here I only plot the virus for different values of theta. Then we also get synchronized oscillations coming out of this. Okay. So would this persist in 2D? So let's look at 2D, what happens here. This is a simulation in 2 dimensions. We inoculate in the center. This is time 1, not time equals 0. So you see how the virus spreads out of the center, forms this ring, and then this ring goes through the entire domain. And if time is enough, it infects everything. If we run this longer, we get the period. So then we get this ring forming, T is 3, and then at T is 13, it starts again in the middle, and then another ring forms, and then it starts again in the middle, and another ring forms, and so on. Yeah, why? Yeah. Yes, exactly. Yeah, very good. And we do here as well. Right, you see what happens very unexpected to us is you get some splitting here. So the peak in the middle, even though it's periodic, it seems to split up into 2 peaks, which then oscillate. And we tried several different numerical schemes, and we tried refining the mesh, etc. And this effect persisted. So we think this is really an effect and not a numerical error. But we have no idea what the bifurcation is, or what the underlying bifurcation is an open question. Okay, so what happens if we run this longer? So now we did at 36 days, but I mean, a computer code is patient, so it can run forever. So then we get this. So we get really very irregular, very chaotic patterns. So here we started with 5 inoculations. We get these rings moving out. But then at every repetition, we get more and more just give me a second, chaotic patterns, and then T is 600, T is 1,000. It becomes very irregular, and it is really moving all over all the time. Herman. Yeah, Neumann boundary condition. Yeah, homogeneous Neumann boundary conditions. Right. So you see here and on this one, if it were periodic, it would kind of come back here, but it doesn't. So it's Neumann boundary conditions. Yeah, aren't they? Exactly. Yeah. I would think so. Absolutely. Yeah. Yeah. I'm pretty sure there is an interaction between the boundary and the inside. The pattern will change for sure, but I'm sure the instability is still there. Patrick. So the question is, if the choice of Neumann boundary conditions is computationally motivated, yes, or biologically motivated, no. So yeah, it's completely a convenience for the computation. Yeah. I mean, biologically, what I show here doesn't make any sense, okay, because we are talking about 600 or 1,000 days, all right? And I said the critical phase of oncolytic virotherapy is in the first 5 days. So this is as irrelevant as it gets, but it's mathematically really cool, right? And so maybe we want to analyze it further. Yeah, long-time dynamics, right? Yeah. Okay. So now we were working on this oncolytic virus modeling, etc. And somehow a colleague at the Li Ka-sheng Virology Institute in Edmonton, Maya Shmulevitz, she heard about our modeling and she contacted me. And she said, hell, I'm a virologist and I'm building oncolytic viruses and we have lots of data and we have also lots of questions. So why don't you use your modeling to help us explain our data? And I thought, wow, this is really cool. Yeah, let's do this. So then I went to her office. I went to her office for our first meeting and I thought, okay, virology lab, this is like a level 3 high security lab, which like fingerprints and showers and masks and whatever. But then I met her in her office, which was just a normal office. Okay, and we talked a little bit and then she showed me this Petri dish here. And she put it in front of me and said, here, this is a virus. I'm like, what? What's happening here? And then, yeah, it's totally harmless for people. It doesn't anything. And it only affects cancer cells. Yeah, right, sure. So, but then these are experiments they do. So the blue is a lawn of breast cancer cells. And then the white are called the plaques. These are infected regions from the virus. So they take breast cancer cells, they infect them with a syringe at certain locations, and they measure the spread radius of these plaques. And then depending on whatever kind of nutrients, etc., they use, they get different sizes of these plaques coming out. So this is the type of experiments they do, and they wanted us to help with the modeling. So I thought, well, we have this wonderful PDE, which does all these fancy patterns. So making some dots is a piece of cake. Everybody can do this. But of course, it is not as easy as you think. So we looked at the data, and then we decided we need to start actually simpler and use the appropriate model for the appropriate data to get through this. And this is a really wonderful story, I find. So let me tell you about it. So the reovirus is a non-pathogenic double-stranded DNA virus. For those of you who are virus experts, there are two types I'm looking at. There's a wild type T3WT, which resides in the digestive tract of mammals. So it's really not a harmful virus. It has anti-tumor abilities and is now in over 30 clinical trials targeting metastatic breast cancer, prostate, colorectal cancer, and currently in 2 phase 3 clinical trials for breast cancer. So this is a really an important target for therapy for therapy development. However, in preliminary evaluations, only 21% of patients respond to the treatment, which means about 80% do not respond to the treatment, and this is a problem. So what can we do to enhance oncolytic activity of the virus? And this is where the Shmulevitz lab comes in. So they mutate the virus to make it more efficient. And apparently they have methods to do this, make targeted mutations, and then measure their binding rates, measure their spread rates, how far they spread, how big the plug sizes are, etc. So doing all this over several years, they found a virus SV5, supervirus 5, which has 5 mutations as compared to the wild type T3WT. And this produces larger plugs. And they found that the binding rate, so the rate the virus binds to the cells, is actually lower for the supervirus. So the supervirus seems to make larger plugs, but the binding is lower. And this contradicted everything they believed in. They always, according to Maya, every virologist thinks a higher binding rate leads to larger plugs. But they found exactly the opposite. A lower binding rate leads to larger plugs. So this was a question. So in particular, her question is there an optimal binding rate? So if I lower the binding rate, I made it bigger. If I lower the binding rate too much, I have no binding. So I get no infection. So maybe there is an optimum. And so this was a question she came to us, if we can use mathematics to find or to help find an optimal binding rate. So this is another set of the data, what they can do. So they can visualize the virus infection using a fluorescent agent, and then they can measure different levels of fluorescence for these plugs. Here's the wild type, here's the supervirus. And when I looked at these images, I was immediately reminded of Dominic's simulations from 2003 or whenever that was. So you also did some modeling of oncolytic virus, right? And they look like this, essentially. So so I think an agent-based model is definitely useful, but I do PDEs, so I stay with PDEs. Okay, so I present you 2 models now for the data analysis. Model 1 is a very simple reaction diffusion equation. So VT is a time derivative for the virus concentration, diffusion coefficient, and a binding term. So just diffusion and binding. And we call this short time because this is in the time, let's say, in the first 16 hours or less, where the virus can bind to cells. It can also internalize into the cells, but the cells didn't have time to produce virus and burst. So this reproduction inside the cells is completely irrelevant for the first 16 hours or so, but the diffusion and the binding is relevant. So we have 2 parameters to find, diffusion coefficient and binding rate. And for the binding rate, they did 1-hour experiments. So they inoculated the virus for 1 hour, then they wash everything out, and they count the virus which has bound. And they repeated this experiments a few times. And from this, we could estimate the binding rate to be 61 per hour for the wild type and 24 per hour for the supervirus. So clearly a lower binding rate than the wild type. Okay. For the diffusion, they did an experiment extra for us. So there's already something where we suggested an experiment and they did it, which is they took a syringe, they put the virus here at the left end, and there's no cells. It is just a medium, and they just see how the virus diffuses through this medium. And then they cut it in pieces, and then they measure the concentration in each of these pieces, and then they get these curves. And so we fit this with the diffusion equation, right? It's just a fundamental solution of the diffusion equation. We fit this there, and then we can estimate the diffusion coefficient from this. And we find this result here. So first of all, we find that there's no difference between wild type and supervirus in the diffusion. And our model fit is 0.01 plus or minus some error. So this works really well. And in particular, then I compare this to other reported values on virus diffusion. So the value for virus diffusion is very critical, and many people or many modeling studies struggle finding a good value for the virus diffusion. So one way to do this is the Stokes-Einstein relation, where you just take the size of the virus and then the Stokes-Einstein relation gives you the diffusion coefficient for a particle of radius r at temperature T in a medium of viscosity eta, etc. There's kind of a certain ratio which you can compute. and this is 0.02. Rioja in a paper for adenovirus found 0.014, and Pollard-Van is 0.01. So if you look at all these values, they're all in the same bulk part. They're essentially all the same. And so I find this is a wonderful confirmation of values which have been proposed earlier for the virus diffusion rate. Yeah.
Is it possible to find threshold for theta where below, for example, the cancer win above the virus?
Yeah, I think absolutely. So you're asking if there's a threshold for theta to see who wins. And these are the bifurcation values, right? So yeah. So if you're below the Hopf point, then you get an endemic equilibrium and the cancer would stay. All right. Oh yeah, spread radius for short time. So now what we can do then is we can compute an effective spread radius. So the spread radius is a radius after which the virus concentration is too small to be measured, essentially 0. So I define a minimum recognizable virus load V min. And then this equation we can solve, right? It's a linear diffusion equation. You use a fundamental solution. You get an e to the minus bt, e to the minus gamma bt term, etc. And you can solve for the value r, where the concentration is below the minimum recognizable value V min. And this gives you this formula. So I spare you the details. But important, it depends on time, and it depends on the binding rate. And this is what I'm interested in. So here I plot how this curves, the spread radius depends on the binding rate. And you see the spread radius goes down as the binding rate goes up, okay? And if the binding rate is too high, in this case 9, then the virus cannot spread at all. It just gets stuck because everything binds. And our cases here, the wild type in blue and the supervirus in red are these values here on the top of the curve. All right. So model 2 now a long time. So now we want to include how the virus infects the cells burst, they produce new virus, the virus is transported, infects new cells. So this is a time scale of 2 days, 3 days, 4 days, 5 days kind of thing. So we include a class of infected cells here. DV and gamma B are already known. So the new parameters are the burst size now, the death rate A, and then there's a nu. And the nu is a percentage of virus that leads to infection. So now this new term is, so yeah, not every virus binding leads to a successful infection of the cell. And they found that about 1 in 100. So if you have 100 viruses binding to a cell, only one of them will actually lead to an infection. So then this factor nu is 0.01, which they published earlier in the paper. Okay. And then for the death rate, they have these experiments where we have hours past infection and number of cell death. And then, yeah, you get essentially, what is this? This is an exponentially increasing function. And you can estimate the rate here, the death rate, and we find A is 0.057 per hour. And this is the same for supervirus and wild type. The burst size, here we have time in hours and released titers of viral particles over time. So here we are interested in the saturation value. This is a logistic curve. We fit it with a logistic curve, and then we are interested in the saturation value here. And then we find these values, 514 for wild type and 732 for the supervirus. Notice this is in a log scale. So here, this is, even though it looks close, there's really a difference here. But maybe there isn't. So if you look at the confidence intervals, then they overlap, right? This plus 114 and this minus 146, these confidence intervals overlap. And this means statistically, we cannot say they're different. Okay, so this is something which comes back later in my talk. But I mean, we think they are different enough, but statistically, we cannot be sure that they are really different. All right, so enough bio. Let's do some math. Who wants to do some math? Traveling wave analysis. So let's see what we can do here. So we take this little model and then we do a standard traveling wave analysis. So we assume that I and V has a form of e to the minus lambda x minus ct. C is the wave speed, lambda is the decay rate of the wave, and then epsilon I, epsilon V are small parameters. So we sit on the leading edge of the invasion wave. I know Ryan is looking, and I think this model is cooperative. So I'm fine doing this kind of analysis. Okay, and let's focus on the C and the lambda. So I'm going to actually use both. So C is the invasion speed. So this tells me something how quickly the virus invades into the tissue. So essentially how large the plug sizes get at a certain time. All right. And so this is what we get. Wild type here, supervirus here. So the invasion speed is 0.044 millimeter per hour and 0.059 millimeter per hour. So the supervirus spreads faster. And the decay rates, 6.9 per hour here and 5.4. So this decays quicker, as you can see in these graphs. And this is a bit more shallow, as you can see in these graphs as well.
Special dimension is 1 or 2?
For this one, it's 1. We just do the traveling wave analysis. Yeah. Okay. Oh yeah. So now we estimated all the parameters. We used a specific experiment essentially for each of the parameters. We have them all now. Now I would like to validate the model with data which I have not used for the fitting. And these are the data I have not used for the fitting. I've shown them to you before, where you have fluorescent markers on the virus particles, which give you very detailed information about the local spread. And this has been then represented here in these blue dots. So these are all the fluorescent markers of the virus particles counted per radius. And we fit this with an exponential decaying function, because we say this is the leading edge of the invasion front. So we fit it with an exponential decay, and this should give us the lambda, the decay rate of the invasion front. And here's what we find. So measured means the red curve, and computed is the one from the previous slide where we did a traveling wave analysis, found the minimum wave speed, and then found the decay rate from the theory. And again, here 4.9 is measured and 5.4 is computed. And I think the agreement is absolutely fantastic. I mean, it's not physics, right? So we don't get 10 to the minus 6 accuracy. It's biology. And to have an order of magnitude agreement is fantastic, I think. So I call this validated. All right. All right, so we have a validated model. We know all the parameters, but I've completely forgotten what I wanted to do. So who remembers what I wanted to do? You remember, what did I want to do?
Yeah, fine. If I could
Yeah, go ahead.
Persuade that mathematics is better.
Right. Persuade that mathematics is useful, yeah. We wanted to find an optimum, right? The original question was, is there an optimal binding rate for this virus? Okay, so now we can go and answer this in this curve. Okay, so this is the main result. And let's look at the red curve first, okay? The red curve here, we plot the binding rate and the invasion speed, which corresponds to the binding rate. So the traveling wave analysis, now we can explicitly calculate the speed from the binding rate. And then we find it's non-monotonic. So it has a clear maximum, and the maximum is marked here with a black dot. The red curve is for the wild type. And the red dot here is the actually binding rate of the wild type. And so it shows if we manage to reduce the binding rate, we can get closer to the optimum of the invasion speed. Now for the other one, the supervirus 5 is the purple curve up here. So there the binding rate is a little bit lower than the maximum. So the maximum is a little bit higher. So if you get closer to the, or if you increase the binding rate, you might get a little bit improvement in the spread rate still. But you also see clearly that the supervirus does better than the wild type does. Now, we notice then plotting these curves that they strongly depend on the burst size. The burst size seems to be a very sensitive parameter. And so this is burst size for the wild type. This is burst size for the supervirus. So we also took the mean value because I said earlier, statistically, we cannot distinguish between the burst sizes. So maybe we take the average, which is a blue line, And then here is the maximum binding rate for the blue curve. Okay, so this is already really cool. So it answers the question, if there is an optimum, yes, and we can quantify the optimum, know exactly where to look for. But then we still got bothered by the sensitivity on the burst size. So we did these curves for many more burst sizes, and then we derived a table like this. So here are burst sizes in the biological range from 500 to 1,000. But we had one case of 750, and the other case was 550. And then we computed the maximum binding rate here, and then the maximum invasion speed here, and the corresponding plug size here. But these are all things which can be measured and which are of interest in the lab. And as we did this, we looked at this for a while, and we found that actually a ratio could be an interesting information. So we built the ratio here of the maximum binding rate and the burst size, and the values are times 10 to the minus 5. And they're all in the same range. They're 56, 58, 60, 55, 56, 57. So it seems like a good recommendation would be to look at a combination of binding rate and burst size in the range of 56 times 10 to the minus 5. Okay. And this is indeed what Shmulewitz is now doing. So they took this table, they went to their lab, and they tried to find any of these optimal combinations through mutations in their viruses. So this means not only did we answer a question, we could also suggest new experiments to the lab, which might be quite useful to do. So, all right, so that's the end of that part. What's the time now? Who's my boss? You are my boss. I still have like 10 minutes or so. Okay, yeah. He's very generous. I will not use 15 minutes, but I might use 10 minutes. So, okay, so now the last part, the work with Morgan van Walsum, where we want to use this model now for treatment. So here I apologize, the variables changed to X, Y, and V because I copied and pasted it from Morgan's presentation. But by now you are familiar with this model. It's the black part here. This is the base model. And now we add lymphocytes. LX is cell-specific lymphocytes, and LV is virus-specific lymphocytes or T cells. So we include the immune response right here in red. And then and then we did a simulation in the Hopf region, so where you get these known oscillations again. And then in green, we have the virus-specific lymphocytes, and in purple, we have the cell-specific lymphocytes. So the immune system now is activated here. Okay, and then we look at 7 different treatments, which all have been discussed in combination with oncolytic virotherapy. So there's a chemotherapy, there's brachytherapy, immunosuppression therapies, active immune therapy is like CAR T cell therapy, fractionated chemo, external beam radiotherapy. So these are all treatments which have been discussed to be used together with oncolytic viral therapy. So I would like to know, at least from the mathematical model which I have now, if this combination makes sense. And okay, so yeah, I'm not going to show you all of them, but we add like chemotherapy terms like this, where E is an exponential term. So this is very standard modeling. So this is how people do it in papers. So brachytherapy, you have a radiation dose, which you add here, and then this radiation term. Immunosuppression, so you add something to the immune system, or actually you suppress the immune system. Active immunotherapy, you increase the efficacy of the immune response, etc., etc. So no point in going through this in too much detail. I'd rather show you these graphs. So these graphs now, for each of the treatments, I show you on the left, oncolytic virotherapy alone. And I use the base parameter values from earlier, where the oncolytic virotherapy does not eradicate the tumor, but rather settles in an oscillatory way on a non-trivial steady state. And then I would like to know if this can be improved by combining it, in this case, with a chemotherapy. So then here is the chemotherapy alone without oncolytic virus. And in purple, you see the tumor control probability. And this is what you should look for in these graphs. So the tumor control probability goes to 1 after about 40, 50 days or so if you use just chemotherapy alone. Now, in combination, we essentially get the same picture. We just gain maybe 5 days or so that the TCP goes up just a little bit quicker. Okay. And this is already interesting, right? So it seems like if the treatment, the alternative treatment alone works, then the combination works. But if oncolytic virotherapy alone does not work, then the oncolytic virotherapy does not contribute much to the overall effect. And this is the same for all treatments we tried. So for brachytherapy, again, these curves match. This one actually doesn't. For passive immunotherapy, same story. For fractional chemotherapy, we get no effect whatsoever. For external beam radiotherapy, again, we get a reduction in the tumor, but the tumor control probability stays at 0. Yeah, so then from this we find when oncolytic virotherapy is not successful on its own, other treatments do not improve it. When oncolytic virotherapy is partially successful, then benefit can be gained from combination treatments. So we did another run of simulations in the Hopf region where we can get improvement through combinations. Yeah, so this then has not been fit to data. It's just for some thought, something to think about. So this is not a finished story then at that case. All right, so let me conclude. First, we talked about the basic oncolytic virus model. In the spatial context, we find very interesting spatial temporal dynamics. Some analysis can be done here, would be nice. In combination with TCP, meaningful conclusions can be made. Yeah. So for the reovirus, we found optimal conditions for the binding rates and the burst size, which explain the experiments and suggest new experiments, which is really nice. And then combination therapies, yeah, one has to look really, really close if they're actually a useful addition to oncolytic virotherapy or not. Yeah, so then I thank you all for listening, and that's the end of my talk. Thank you.